So you're probably wondering, well, how are you going to know when gamma ray is happening or not? So typically how it would look, especially if you're doing something like this, that's fill in the blank, you're going to notice that there's going to be an additional blank, right? So meaning that there's going to be, if you have alpha or beta and there is an additional blank, like something else is also produced when that reaction's happening, it's going to be your gamma. Okay, so same with this, your beta. If there was another row here and we weren't sure what this is, because beta is occurring, you can also have gamma radiation happening at the same time. So, just to recap, so gamma is not really a particle at all. We call it a particle because it's essentially radiation. So remember this 2 does not matter. The reason why that 2 is there is because this particular reaction actually lets off 2 of these high energy wavelengths. So really, when you're writing out the reaction for me, I don't expect you to know if it's 1, 2, or 10. You're just going to be putting this symbol for gamma particles, okay? So it's a high-speed electromagnetic wave of energy. It has no mass and no charge. It's just simply energy. So it never happens on its own. It's typically with alpha or with beta when it is in fact occurring. So this is a nice summary chart of the different, the 3 different radiations that we've looked at. So we have alpha, beta, and gamma. So the symbols are there. So in terms of the particle size, so this is all based on relative mass. So remember that the alpha particle has a mass of 4 because it's 2 protons and 2 neutrons. The electron actually has essentially very little mass. If you remember when we're talking about protons, neutrons, and electrons before, the electrons are essentially so light we almost call it a 0. It's not 0, but it's very, 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 very small. And actually gamma ray in fact is 0, a true 0, because it has no particle at all. It's simply energy. So just to summarize, what happens to the alpha radiation, what happens in the nucleus? The mass number goes down by 4 and the atomic number goes down by 2. We're losing 2 protons and 2 neutrons from the overall nucleus. Beta particle emission, what's happening here is a neutron is converted into a proton, which means the atomic number goes up by 1 and the overall mass does not change. Gamma ray particles do not change the nucleus at all. This happens either with beta or with alpha. Now in terms of the particle itself, how essentially what we mean by penetration here is talking about into essentially human flesh. So how far can it essentially go through tissue? So alpha particles actually cannot go into human tissue at all. So your skin is enough of a protection barrier because it's it's such a low danger level. It's very safe to work with. So older smoke detectors that you might find in your house actually use alpha particle emission in the way that it actually functions. So of course they're happening in your house. It's fine. Any cell tissue is enough to protect us from the radiation. Beta particle can go through skin, through tissue. However, anything that is over your skin can protect you. So if you're wearing clothes, or if you're wearing a lab coat or any sort of covering material, gloves, that is enough to protect you. However, gamma ray emission is actually very strong in terms of its energy and danger level. So gamma ray is enough to actually cause mutations in tissue cells to the point where it may cause cancer. So in terms of when working with gamma radiation, your clothing is not enough. You need to have a lead apron on. So if you've ever it's very similar to when you're working with x-rays. So if you've ever gone to the dentist and you know they're taking an x-ray of your mouth, usually they'll put that heavy apron on you. to protect your torso from the radiation, and that's typically made out of lead. So there's a layer of lead in there. That's why it feels so heavy when it's on your chest. So of course, so it's kind of increasing in level of danger here as well. Now, so moving away from radiation decay, so alpha, beta, gamma, we're looking at two other types of nuclear reactions. So one is called nuclear fission. Fission is essentially when you split, maybe you've heard of it before where it says it's splitting an atom. This is where you take a larger nucleus, and what's happening here is this little blue dot is representing a neutron. Okay, this is representing a nucleus. So what happens is a neutron is essentially fired at a heavy nucleus that then causes this nucleus to split into two or more fragments. So for example, here we have an isotope of uranium-235. This neutron that's coming here will cause this to split, and what happens is now we have two other resulting, you have more particles that are made as a result of that, which is these two here actually. But when the splitting of that atom happens, it's actually the ricochet effect that matters to us here. So when this splits, it actually causes little neutrons to fly off from that one bigger nucleus. So what happens is those then can now cause a chain reaction. So this one here, maybe it doesn't hit anything. Maybe it hits other uraniums. So this uranium, I want you to notice, uranium-238 did not split. The reason why is because uranium-238 is not a radioisotope. Remember, all of these nuclear reactions can only really happen if you have an unstable nucleus. So uranium-238 is not unstable, which is why it doesn't split. However, if it hits another uranium-235, it splits and causes more chain reactions with more neutrons that will cause more to split. Now, when this splitting occurs, a ton of energy is released as a result of that. So this is actually a huge amount of energy that is essentially can be used to harness things such as nuclear energy, right? So like at a nuclear power plant, you'd have a facility where this would be occurring. And of course, this energy would then be used to spin a turbine and eventually cause energy generation. So this energy that's let off is incredibly powerful. So this is definitely not alpha decay. I'll tell you that. The other type of nuclear reaction is nuclear fusion. This is actually the same type of nuclear change that is happening that lets off energy in the sun. So what happens here is instead of splitting an atom, two smaller atoms will come together to form a larger one. So the exact reaction that's actually happening on the sun is there's two isotopes of hydrogen. Hydrogen with a mass of 2 and hydrogen with a mass of 3, which we actually already saw before when we talked about the volcanoes. So what happens is when they come together to make a larger nucleus, and this shows this here, it's creating helium. Hydrogen and hydrogen come together to make an atom of helium. But when this combination occurs, a ton of energy is released. So the hydrogen eventually becomes helium. This is what's happening. So the sun really is a giant sphere of hydrogen gas that is continuously doing this fusion reaction. However, eventually when the hydrogen runs out, the sun will no longer be able to generate that electricity. But don't worry, we have energy. So thermal energy as well as light energy. But don't worry, we have about 8 billion years. The sun's got a lot of atoms in it still. We'll be fine. We will have enough. I'm more worried about us us on Earth here, not so much. I'm not worried about the sun running out of energy at any point in time soon. Okay, so that is looking at this. So in terms of these last two, we looked at fission and fusion. You should know the differences between the two, but I will not ask you to write out the reactions for these. However, your alpha, beta, and gamma, you will be expected to know how to write out those reactions.